One reminder is that some of the written assignments this week, one is due this afternoon at 5 p.m., the other on Thursday at 5 p.m. Those written, not the written assignments, web work assignments, not the written one. So I guess it's web work 8 due this afternoon and web work 9 due tomorrow afternoon. I think that you're going to find these web work assignments pretty familiar. They concern a lot of material that we've already covered, which concerns basis of vector spaces, questions about finding bases for things like the null space, the column space, the row space for a particular, associated to a particular matrix A. It's kind of where we're at. Make sure you're on those and doing them. If there are issues with completing them, just let me know. Another announcement is there's a written assignment 3 that's going to be due next week. I'm going to make some changes to the written assignment, so you shouldn't really invest too much time in the written assignment that you see posted. I'm going to wind up leaving a couple of questions on it. A lot of the questions about basis and coordinates I'm going to wind up removing. I'm going to replace them with questions about orthogonality, just a couple of questions which hopefully familiarize you with how orthogonality wants to work. I'm also going to put a couple of the questions from the previous written assignment on this written assignment to give people a chance to kind of mess with them a bit more. I think the last 2 questions on written assignment 2 are pretty hard. If you turned in the written assignment 2 with those questions, I'll wind up commenting a little bit on your submission, but I'm not really going to grade those on written assignment 2. I'll grade them on written assignment 3. You can play around with the questions that were 5 and 6 on written assignment 2 on written assignment 3, and that's when I'll look at them. So we've talked a little about those problems in class. I've talked a little about them with people during office hours. So I guess this week, if you want to think or rethink about those questions, feel free to drop by office hours or ask or something like this, and I'll be happy to talk about them a little bit. Try to give you some hint or direction on those questions if you're struggling with them. So I guess that's kind of where we're at right now. At the end of the week, we'll be through with about half of the course. Progress in the course seems pretty good. We've already talked about some major topics in linear algebra. Probably some of the more important topics, the things that you're liable to remember over the long term, are things that are associated to the notion of basis and dimension for a vector space. So far, we've mostly concerned ourselves with things like Rn, because I think those types of vector spaces are the most familiar. We might move on to more abstract types of vector spaces, but the truth of the matter is that if you're dealing with any finite dimensional vector space, it's basically just Rn with a standard basis, with a suitable choice of basis for the vector space that you're discussing. So finite dimensional vector spaces, their structure is like that of Rn. So a lot of the features that Rn has, finite dimensional vector spaces also have. So Rn, as we now know, not only is a vector space, but it's also an inner product space. There's a notion of an inner product which tells you a little bit about how big vectors are, tells you a little bit about when they're at right angles, allows you to say something about, in fact, the angle between vectors, if you remember some stuff from Calc 3. So all of those things sort of want to characterize Rn. So it's very special in that it has all these properties, but anything like Rn is probably going to have those properties as well. So when people generally study linear algebra at the outset, they tend to restrict their field of vision to finite dimensional vector spaces because those are the ones that are most familiar. If you want to study linear algebra a bit more, one direction that you can go is you can start to think about the properties that infinite dimensional vector spaces have. That's more of it's field. There's an entire field which is related to this. It's called functional analysis, in which you see a lot of the stuff that we're talking about right now, but more general versions of it, which are appropriate for considering vector spaces which have a basis which can be described with a finite number of vectors. Function spaces are an example of this, and I think we gave a couple of those as an example of abstract vector spaces last week, kind of passed over them as examples. But in the long run, it's something to think about. Right now in the class, we've talked about basis and dimension. As of yesterday, I guess as of the first couple of days this week, we talked a little bit more about the internal structure of things like Rn. When you have an M by N matrix, the most important thing about the discussion so far is that a matrix A sort of acts like a function. So I'll write some of this down so it's clear, or it's hopefully clearer than just me saying it. So an M by N matrix A acts like a function from Rn to Rm. Now, when you write something like that, we're saying that the domain space for, so I guess I should give the matrix a name, and M by N matrix A acts like a function from Rn to Rm. We're saying that the domain space for A is Rn, and the range of A is contained within Rn. So how does this map actually work? If a vector V is an element of Rn, then a V is an element of Rm. So this sort of statement doesn't say too much because we're not really describing very much about the characteristics of the function, but we just have this picture where we might represent Rn as some sort of blob, and a vector V is contained within it, and Rm might be represented as this other blob, and the vector V goes to the vector AV. So I'll give you an example which might make this more concrete in just a second. And if that's all we really had to say, there wouldn't be too much to say about matrices or vector spaces at all. But it turns out that the properties of vector spaces, in particular properties of A, allow us to describe a little bit more about certain key subspaces of these two vector spaces, Rn and Rm. But we've already done this. Again, what are those vector spaces that I'm talking about? Well, subordinate to A, within Rn, we have the null space of A, and we have the row space of A. So I usually write the row space as R of A transpose. When you write things like R of A transpose, what you're saying is that you're just putting the elements in the row space into the proper form by converting them from row vectors to column vectors. When you talk about A transpose, basically A transpose is A but flipped on its side. The columns of A transpose are the rows of A. So when you talk about the row space, you're really trying to describe the contents of a subspace consisting of all linear combinations of the columns of A transpose. If you think about it for a minute, you realize that those are the same guys. If you just flip the rows of A, that's into columns, that's what that is, in the sense that spans that. And within Rm, we have the column space of A, and we have one subspace that we haven't really talked about, but maybe it's not so surprising that I would write this down. We also have the null space of A transpose. So I guess A transpose, if you think about what A transpose is, if A has M rows and N columns, A transpose has N rows and M columns because of the role of the columns and rows are flipped. So A transpose is a map from Rm to Rn. It's usually not the inverse of A. Sometimes it is, but those are some special cases. When we're thinking about both Rn and Rm, and we have a matrix A, there are basically four subspaces that we're thinking about. And we've talked explicitly about three of those. Discussions about the null space of the transpose of A are a whole lot like discussions of the null space of A. You can sit down, you can find a basis for the null space of A transpose. It's going to wind up being what you think it is. And by symmetry, the orientation of the null space of A transpose and the R of A, the row space of A transpose, will be the same as what's going on in Rn when we're dealing with the row space of A and the null space of A. So by symmetry, because, all we're doing is we're just flipping the matrix around and thinking about the other side. But so we have all that, but even more than that, we basically have descriptions. We have descriptions for all of these vector subspaces of Rn and Rm. What I mean by description is we can compute, we can efficiently calculate a basis of vectors for every one of these subspaces. So, and even more than that is true, there's a notion, there's an inner product on Rn and on Rm, which gives a sense of geometry on those vector spaces. So the vector subspaces that we actually have of these vector spaces not only are contained within Rn and Rm, even more than that is true, they're orthogonal. So within the vector spaces, things like N of A and in the row space of A, R of A transpose, are orthogonal complements. And something similar is true for the null space of the transpose of A and the column space of A within Rm. So if you think about it, we've accomplished quite a lot. If you think about where we started, we start with some theory of equations, and now we're talking about functions from Rn to Rm and some properties that those functions have. The modern view of linear algebra, usually characterizes matrices as something as a function from Rn to Rm, and so you'll see this type of thing over and over again. So that's kind of where we are right now. Subordinate to a matrix A, we have a structure theorem. We basically have structure theorems for Rn and Rm. We can sort of subdivide them into these complementary subspaces for which we can write down a basis. And that's pretty interesting. And it turns out that the decomposition that we have, the splitting of Rn and Rm into these subspaces allows us to write down any vector within Rn as a unique linear combination of a vector coming from so if we're thinking about, say, the Rn, any vector in Rn can be written down as a unique linear combination of an element from the row space and an element of the null space. So this is the nature of the conversation. So that very blobby picture that we started with has been refined quite a bit. And it looks more like this, and it's a wonderful picture. I think I've seen this in various places. It's a picture that looks like this. You can use that little box to designate the row space of A. We can use this little box to designate the null space of A. Over here, we're thinking about Rn. And over here, we're thinking about Rm. And over here, we've got what we usually think about as being the column space of A and the null space of A transpose. The point of intersection right here represents the zero vector. So if we view over here, this diagram, if we view what's going on over here as some general version of Rn, it's just some abstract picture of Rn. Obviously, I can't draw Rn for very many n. If we view the range space as being contained within Rm, what we're really saying, I guess, with all of this is that you have a vector x here, and it's not necessarily, in either one or the other of these spaces. You can decompose that vector into two pieces. You can break it up into an element coming from the row space and an element coming from the column space. And it turns out that the action of A will send this guy right here, the x, into AXS, and it will kill the element in the null space. And so what's happening with x is if x is a linear combination of those two guys, all that happens is x goes to this guy. So this is an example of something called the commuting diagram, where basically if you take x, you split it, the piece associated with the null space of A goes to the 0 vector. The only piece that survives is this piece that comes from the row space. That's a nice structure theorem. It's surprising that you can get as much mileage out of the idea of a linear transformation and some basic facts about vector spaces about Rn to get this. The picture is not accidentally arranged. Notice that in the image, it looks like things are kind of occurring at right angles. Like you can only do this to a certain degree, but it's sort of like you have this and you have this. You want to think about them intersecting only in a single vector, in the 0 vector, and the same thing is true over here. But they intersect at right angles, so they're not just. It's not just any old decomposition of Rn. It's breaking it into these orthogonal pieces. It's a nice idea, and so I think it's a nice theorem. It's a nice place to kind of stop momentarily, thinking about what we're doing with matrix algebra. We started from a very simple point of view. We get this complicated idea that a vector space has, if you have a matrix A vector space kind of has this unique decomposition into complementary subspaces, and elements from the subspaces kind of comprise all of the vector space Rn in some way. Of course, this depends on the choice of A. You have a different A, you get different decompositions. One nice question to ask, I guess, is if you have A and if you have a matrix B, which is a row equivalent to A, how does the picture change? That's a nice question to ask. Maybe I'll ask it on a written assignment at some point in time. But I'll probably make it concrete. So that's kind of where we're at right now. At 10:20, I'd like to stop and have people kind of do an exercise which wants to support this type of picture. I'll write down the exercise. You can take a few minutes to do it, just to kind of warm up, to think a little bit about maybe it would help make the image that we're trying to draw a little more concrete. So here's the example. So you can do this. Take a few minutes to do it. Let A be equal to the matrix 1, 0, 2, 1, 1, 4, 2, 1, 0. So several things to do. The first thing, find a basis for the null space of A. Second thing that you might do, find a basis for the column space of A. So we're sort of decomposing what Rn into these two pieces. Verify that these subspaces of Rn are, I guess what I mean, are orthogonal. They're actually orthogonal complements. Should be T right here. And maybe the fourth exercise is write the vector 3. A bit more room. Write the vector 3, 3, 3 as a linear combination of an element from the null space and an element from the row space. Give that a shot. It may take a few minutes. You may have to go back and try to remember some facts about how to find things like the null space and the row space. But it's worthwhile at least doing the first few, then maybe we can talk about 4. So I'll put it back up. I'll turn my video off. Take about 8 minutes to do it. Go through it, think about it, find a basis for these two things, show that what you're dealing with, show that the subspace is spanned by your bases are orthogonal. They're in fact orthogonal complements. It's a bit stronger than saying they're orthogonal. And then take a vector and write it down as a linear combination of a vector from the two subspaces, a combination of them. So let me turn this off. Take a few minutes to work through the example. All right, good. So back to the example. Remember that the goal is to just sort of try to make concrete these notions of these subspaces of Rn and Rm. In this case, we're only looking at finding a basis for the null space of A and the row space of A. We're doing a couple of more things. So how do you actually do that? You probably remember this, done this a number of times, but it's worth doing again. I won't do all the calculations here. So for the null space, notice that the null space of A is the same subspace as the null space of U, where U is the reduced row echelon form of A. So the reduced row echelon form of A, for us, in this example, is this guy right here. When we try to solve, I guess I'm letting that be U. When we solve, we try to solve the equation UC equal to 0. Because of the structure of the matrix, we find that C is the 0 vector. So what does this mean? This means that the null space of A is just the 0 vector. So this example is a little bit different than others that we might have done recently. Lots of times if you have a matrix, it's got a non-trivial null space, but that doesn't happen in this case. So are people with me so far? Null space of A is the same as the null space of the reduced row echelon form of A. And we find in this case that the reduced row echelon form of A is trivial, 0, because the matrix totally reduces. So that's it's an interesting fact. What does the basis look like in this case? It's sort of goofy. It's just the 0 vector, right? It's got this trivial empty basis somehow. So what is a basis for the row space of A of T? Just pick in this case, just pick the vectors 1, 0, 2, 1, 1, 4, and 2, 1, 0. So notice what I've done is simply to select the rows of A as my basis. I didn't really look at the standard basis, though you could have done that as well. You could have picked the rows of the reduced row echelon form and gotten the same R3, right? So when we're thinking about the row space, and you conceptualize it as the column space of the transpose of A, lots of ways to write it down, but what I wrote down is certainly a suitable basis for the row space of A. It's just the rows of the original matrix. The row reduction process is basically revealing that in the sense of row vectors, these vectors are linearly independent. There isn't anything redundant in the rows. So you're not really writing one row as a linear combination of the other rows. You can't get away with getting rid of any of them. You can pick all three of the rows, or at least you can pick the transposes of those rows as your basis for the row space. Couple of things to notice about this. Just write down this point. Cases like this, we often say.
I have a question.
Yeah.
What would the difference be between, you said you could use that, or you could use like, you said the standard vector?
Yeah, so when
Are you
you're.
referring to like the null space of A?
I'm talking about the row space. I'm talking about the row space. So the row space of a matrix A is going to wind up being the same as the row space of the reduced row echelon form of A. So the reduced row echelon form of this matrix is just the identity matrix. So another basis for the row space is 1, 0, 0, 0, 1, 0, 0, 0, 1. So these are two different bases for the same subspace of R3. If you think about it for a minute, though, you realize that those two bases for, those two bases both span, those two set of vectors both span R3. The rows of A are linearly independent. That's what the fact that the matrix reduces to the identity matrix means, that it's impossible to write a row of A as a linear combination of some other rows of A. If it's possible, if the rows of A in the sense of row vectors are linearly independent, what you're going to find in cases like that is that you're going to get a zero row or something like this, but that's not what's happening. Matrix is a full rank. It's a square matrix with rank 3. It's a 3 by 3 matrix with rank 3. All of the rows and all of the columns are linearly independent. But I guess another point out, one thing to point out is that, maybe what I wrote down is a slight deviation from the process, but it's fine in this case. You could write down the vectors 1, 0, 0, 0, 1, 0, 0, 0, 1 as your basis for the row space. That's also fine.
So why, I was kind of wondering why it's like, I guess the same if you use just like the rows of A versus using like the row reduced form of A.
Why is, so in this example, the reason that it's the same, in just this example, is that the rows of A are linearly independent. And so when you consider them as columns, they still are. So, if you just take the original what is establishing that is that if you row reduce the matrix, you don't get a zero row. The fact that none of the rows of the reduced row echelon form of A is the zero row means that it's impossible to write down any row of A as a linear combination of any of the other rows. So in general, the row space is defined as the subspace of Rn, in this case R3, which is spanned by the transposes of the rows of A. So when we're trying to write down a basis efficiently, we usually are not in quite this situation where the rows are linearly independent. So if we're trying to write down a basis for the row space of A, what we typically do is look at the reduced row echelon form of the matrix, and you look at how many rows survive, the elimination process. You can pick out those rows and use those rows in the reduced row form as a basis for the row space of A, because elementary row operations don't change, or elementary row operations are such that they are, they don't change. If you have some set of vectors which span, some subspace, and you have another set of vectors which span a subspace, but the two sets of vectors are linear combinations of each other, I guess what I want to say is that, then either one of them suffices, I guess is what I mean. So when you look at this example, you can check that, anything in the set of 3 vectors I wrote down when I was just looking at the rows of the original matrix, and anything that you would write down if you look at 1, 0, 0, 1, 0, 1, 0, 0, 0, 1, it's exactly the same subspace. And the reason is that the vector, if any vector in one of the sets can be written as a linear combination of the vectors in the other set, and vice versa. When something like that happens, you don't care which set of vectors you use, at least if your goal is just to write down a basis. And the process will typically generate a set of vectors coming from the reduced row echelon form of the matrix, but we don't even need to bother with that in this case, because the vectors that you're talking about that I wrote down are linearly independent. And by definition, they span the row space. So they're a basis for the row space, if that makes sense. So are the vectors 1, 0, 0, 0, 1, 0, and 0, 0, 1. They're both bases for the same subspace. It's sort of a funny subspace in this case because it constitutes all of R3. The dimension of both of these bases is pretty clearly 3.
Okay, thank you.
Okay. Whoops, sorry. Right. This is sort of a funny situation. It's pretty clear that any vector in the row space of A is orthogonal to the 0 vector. Just check inner product. And if you wanted to write down, if you really wanted, to represent 3, 3, 3 as a linear combination of a vector in of A, the null space of A, and a vector in the row space of A, then you just would be solving the system of equations where you put the basis for the row space up. So you'd just be solving AC equal to 3, 3, 3, where A were the columns of A are the elements of the basis for the row space, because the columns, the null space is basically 0. So problems can be a little more complicated when you don't have a trivial null space, but the null space is trivial in this case. And when you solve an equation, that looks like, that's a point we're going to get back to today. When you solve an equation that looks like AC equal to some vector, really all that you're doing is you're trying to represent the vector B, in this case 3, 3, 3, as a linear combination of the column vectors of A. And so you solve that equation in the normal way. Basically, you just take the transpose of the matrix A. That's what A actually, I've got too many A's around, but you take the transpose of A, and then you solve the equation. I guess I should, maybe it's just as well if I write it this way. You solve the equation A transpose C equal to 3, 3, 3. That way the columns of A transpose are pretty clearly the elements of the basis are AT, so I don't really even need to write that. So in general, trying to find, the decomposition of a vector might be a little harder than that. But another thing, and I think we mentioned it toward the tail end of yesterday's class, is that if you have a basis for the null space of A and you have a basis for the column space of A, if you happen to have non-trivial null and column spaces, then when you put those bases together, you wind up getting basis for the whole space. And so probably you'd probably arrange to do the problem that way. So that's kind of how you handle a question like that. But it's a nice structure theorem. I like it. You know, it's the picture of the structure theorem is nice. It's basically giving you things like rank plus nullity theorem. That's usually called the fundamental theorem of linear algebra, as it relates the dimension of the column space, the dimension of the range of A, with the dimension of the null space of A. But a lot of the stuff that we're talking about is not maybe surprising if you think about what we've done so far. You know, the concepts like rank plus nullity, or even the picture that we have that we're seeing, are simply recasting what we've already done many times. If you started with a system of equations and you wind up with some number of free variables, columns in the reduced row echelon form of A associated with free variables will account for the basis of your null space. And columns that are not associated with free variables, columns in which there are non-zero pivots, will tell you something about the column space, and those numbers have to add up to the number of columns, clearly. So, you know, it's called the fundamental theorem of linear algebra, but maybe it's not that hard to imagine seeing it even in week one. It's a little bit harder to see when you're talking about some generic linear transformation, but, you know, in a sense, if you take a linear transformation and think about, well, we'll talk about that later. So before I move on, does anyone have any questions about what we've done so far? Just dealing with matrices. We have some decomposition of Rn and Rm subordinate to the choice of matrix. Natural questions are, you know, okay, if you have a different matrix, do you get a different decomposition of Rn? Do you get different null spaces and row spaces? Well, you know, clearly depends on the matrix, right? If a matrix A, you know, an interesting question is I guess this, and I might actually ask this because I think we're sort of in reach of having an answer to it. If a matrix A is row equivalent to some other matrix U, would you get a different decomposition of Rn? Are the null spaces and row spaces different, or are they the same, and why? That type of question is kind of interesting to ask, interesting to think about. You probably already know the answer. So with all of that in mind, that's kind of where we're at right now. You know, the examples, a summary of some stuff we've talked about. It's always worth going back and talking about these things because I think, you know, with all the terminology, it's probably easy to get lost. I'll change written assignment 3 to, I think, involve some of these concepts, so you'll get some practice in handling, you know, more concrete problems than just pictures. You know, so with that in mind, I'd like to try to move on to new material today. I'd like to think a little bit about how we might exploit the geometric structure of Rn, which we gain by thinking about inner products. Today we'll look at a particular application, which I think will be familiar to many of you, if, you know, provided that you've taken a basic statistics course at some point in the past. Tomorrow, I'd like to we'll think more about one particular aspect of the discussion toward the end of class today, which will come up, you know, hopefully, depending on how the time goes. So let me go back and share the screen. I'll have to occasionally fill in some details, but I don't think the details are too bad. So the title of today's set of slides is Projections in Least Squares. Least squares, or ordinary least squares, is something that many of you, I think, might be familiar with, because if you're dealing with ordinary least squares, you know, the classical environment where you're trying to find a line of best fit through some collection of pairs of points that come from some kind of survey that you're doing, you know, usually you subordinate the calculation of the line of best fit to some computer. But today we'll talk a little bit about the theory behind least squares, where it comes from, and in some sense how it is, or how a computer is even capable of producing such a line. So we'll talk about the machinery under the hood a little bit, and how that comes from some geometry on Rn, which we get from the inner product. So we take advantage of the inner product on Rn to handle systems of inconsistent equations. So you might think about, you know, the entire talk today as just sort of giving you a theory of inconsistent equations. So far in the course, we've limited ourselves to situations in which an equation either has a solution or an infinite number of solutions. We've kind of ignored the situation where the equation that we're getting is inconsistent. Inconsistent equations will want to occur when you have more equations than unknowns. When you are trying to do anything in the real world, when you're making measurements, this occurs all the time. Regrettably, in some sense, we still won't be able to solve inconsistent equations. I mean, of course not, because they're inconsistent, but that won't really be the goal. Rather, we want to come up with an approximate solution which is reasonable somehow. There are many reasonable solutions to the inconsistent equation problem, but we'll talk about the most well-known solution today. So the first few set of slides are sort of the technical tools which are necessary to try to handle inconsistent equations. It will become more clear, I think, why these tools are necessary when we get into the discussion a bit later. So the first thing that people usually talk about when they're talking about inconsistent systems of equations is called vector projection. If you're thinking about vector projection, if A and B are vectors within some Rn, like you see in this picture, the goal is to find a vector A1 within the span of B, which is at a minimum distance from the vector A. So that vector A1 is known as a projection of A onto B, or better yet, it's a projection of A onto the span of B. So there are a couple of ways maybe of viewing the problem, but I think this image this is an image. What you see below is an image of what we want to find. You'll notice that you have a vector B, a vector A, and then two other vectors A1 and A2. If you're thinking about this picture for a minute, the vector A2 is clearly orthogonal to the vector B. It's orthogonal to the entire span of B, in fact. And the vector A2 is such that it is when added to A1, it will produce the vector A. So we're saying that A1 plus A2 is the vector A in this image. So the goal is to try to say something about, first at least, to try to say something about the projection of A onto B, which involves saying something about how you come up with a formula for the vector A1. So that's the goal of the next few minutes. Talk about that, talk about that in more detail. But again, do you see what we're trying to do? Sometimes this problem is addressed in Calculus 3. Often it is, I guess it's part of the content of the course. So those of you who've taken Calc 3 probably already know what a vector projection looks like. It's worth going back and talking about it a little bit using the symbolism that we're using so far in the course. But it's sort of the shadow of the vector A. We're projecting it down onto a subspace of Rn. And the goal is to find some kind of algebraic formula for A1. The geometric problem is actually pretty easy to solve if you think about it. It just involves thinking about how sine and cosine work for the angle between the two vectors. So one approach to this problem is to do that, and that's usually what people think about in Calculus 3. But here I want to strive for a solution which is more in terms of the vectors themselves, if that makes sense. So, back to the image. It's a pretty plausible picture that minimizes some length of A2. A2 in this case represents the directed difference, the directed distance between A and the vector B. We're thinking about our choice of A1. And so I think that one correction, I think. I want to write this as B. In the picture, the directed distance between A and B appears to be the smallest because A2 appears to be minimized in length for that particular choice of A1. So if you go back to the picture, if you made A1 a little bit longer, it would still be in the span of B, but most likely the distance between the tip of vector A and wherever A1 ends will not be as small. So, I mean, you can pick a lot of vectors in B onto which to project A, but really we would think that there's only one which minimizes the size of A2. So that's the goal. The vector A2 is just A minus A1. We appear to want an A2 that is orthogonal to B. Remember that symbol means that means something to us. Algebraically, we want to be able to solve this equation right here. So what does this equation mean? This equation is merely saying we want A2, the dot product of A2 with B to be equal to 0. That is, A2 and B need to be orthogonal, and that will be the size of the vector A2 will be the minimum distance that we seek. One more note. It certainly appears that A1 is a multiple of B, and this is because A1 is an element of the spanning set of B. So in our equation, we can replace A1 with a multiple of B, and that's a productive direction because we can write down more clearly what this is. So if you solve this equation for K, you wind up with what's on the next slide. You get an equation that looks like, you get some value for K that looks like this. So the value of K in this context is the so-called least square solution to this problem that we started with. The value of K is the constant you would need to multiply B by, or it's the amount that you would need to scale B by in order to get the vector A1, and it is chosen in such a way so that it minimizes the size of A2, which is the gap between A and B. So, we can talk a little about solving. We can talk a little about solving the equation. It's a bit of algebra. It may not be that interesting to discuss. But in the end, we get a formula for how to do it. The vector KB is called the projection of A onto B, or better still, it is the projection of A onto the span of B. So at least the problem when we're dealing with the problem that we're running into when we're dealing with a vector A, which is not in the span of a single vector, can be solved. We can arrange a choice of projection which minimizes the gap between projection and A. The gap between B and A is minimized with that choice of A1. And the result of, and again, the geometric intuition that we're using to sort of justify to ourselves why that makes sense is that in the original picture of the triangle, the choice of A1 we want to make is a choice which makes A2 the smallest, and that's going to happen when A2 and B are orthogonal, when they're at right angles. Any other choice of A2 that you're drawing is going to result in a larger magnitude of A2. The straight line distance or the perpendicular distance is really the one that you want. Are there questions about this so far? So this is a problem. If you've taken Calc 3, this is a problem that many of you have probably already seen. You might have seen this formula in a different form, but there it is. I think in Calc 3, you talk about use symbolisms that look like the proj, P-R-O-J, of B onto A, or of A onto B, which is what we're talking about right here. That's the typical notation, which is, I think, used in calculus books. So that's the idea. Anything so far? Is this okay? That's the idea. We can have a formula for it. Now, we want to extend this idea. Well, I guess before we do that, we might want to spend some time doing it. We can make our intuition precise in this case using calculus. The A2 in our image represents the directed distance between vectors A and B. The goal is to minimize the difference between, is to minimize this. But what's A2? It's just the difference between it's just the distance between A and the vector A1. But the vector A1 is K times B. So we're trying to minimize in the system, if we're using the techniques of calculus, we're trying to minimize something called E2, the error term, E squared. That's this guy right here. E squared, when you write every detail down, when you write down a symbol like this, you're really just talking about the dot product of a vector with itself. So the thing you're trying to minimize is a quadratic function of K. And that's probably worth verifying at some point, but I'll probably leave that to a written exercise. So when you're trying to minimize E squared, when you write down E squared in detail, you get something that looks like this. One note about that's probably worth making. This thing right here is the same. In fact, is sort of defined as the product of these two matrices. So basically, you just sort of multiply these things out and figure out that you wind up with something that looks like this. And so you get, if you multiply it out, the transpose commutes over the difference. So you get KB transpose minus A transpose times KB minus A. Distribute and realize that the cross term that A transpose B is the same as B transpose A, and you wind up getting this equation right here. One thing that I would point out, and this is actually quite important for the more general version of this, is that the error term that you see is quadratic. The reason why the error term is quadratic is because it comes from an inner product of a vector with itself. And so if you're trying to find some unknown number k, you have to solve a quadratic, you have to minimize a quadratic equation in k in order to be able to produce the value of k that is the one that we want. So moving beyond the geometric intuition, we write down the error term that we want to minimize. We figure out what that error term is in terms of k, and then we proceed to solve a minimization problem using the tools of calculus. So how does that actually work? If you're trying to use the tools of calculus to solve this minimization problem, you have to remember that B transpose B, A transpose B, A transpose A are just numbers. So when you take the derivative of something like E squared, you take that derivative relative to the vector K. Now, what I'd like to talk about what I'd like to have people do just as a review of calculus is just solve the minimization problem. If E squared looks like this, that the next project is worth spending maybe a minute doing it. Find K, which makes E squared the smallest. So I think everyone in here has taken calculus or calculus 1, or is maybe in it. Maybe, I think probably certainly it's taken calculus 1. So this is a problem from Calc 1. It's an optimization problem. I'm trying to minimize something. So it's worth doing. It's a problem from calculus. Go ahead and do it. Take about 3 or 4 minutes. Solve the equation for the k that minimizes, find the k that minimizes the value of the error term. A couple ways to do it. You could use calculus. If you don't like calculus, you could put the parabola, I guess, in standard form and find where the vertex was. Maybe that's it's not really gonna, that's not gonna really extend easily to the more general case, I guess. Right now, about 11:02. Take 3 or 4 minutes to solve the minimization problem, and then we'll come back and describe how it might be solved. Okay, so going back to the problem, if we want to solve the minimization problem using calculus rather than just a picture, the goal is to find a value of k which makes E squared, the square of the error, the smallest. How that might be done. So when you take the derivative of E squared, you get something that looks like this. So you're taking the derivative with respect to the variable k. So the derivative of E squared is 2 times the number B transpose times B. Remember that the k in this case is the thing that varies. That's the weight we're looking for. That will minimize some error term. The constant term, the A transpose A, you take the derivative of a constant, it's equal to 0. So you wind up with a derivative of E squared that looks like this linear function. Again, from Calc 1, maybe that's not surprising. So to find the value of k that minimizes E squared, find the critical number. When you find the critical number, you solve this equation for k, and you see pretty quickly that the critical number ought to look like that. So when k is equal to this thing, the derivative of E squared is equal to 0. So that's going to be the guy. If you're really being careful about it, I'm not being that careful about it, but later we might want to be. It's worth probably think about second derivative test to show that we're at a minimum. You have to think a little bit about why the second derivative test would work that way in this context. But the second derivative of v squared is clearly just 2 times b transpose b. B transpose b is just the length of b, and presumably b is not the 0 vector, so it has a positive length. And because of this fact, the value of the second derivative is going to be positive, which means the function is locally concave up around the value of k that we just found. That means that we're dealing with the vertex of the parabola. So, that process that we just described is in a way how, that's just sort of a small version of how the actual proof of the so-called least squares theorem actually works. You basically write down some equation, some sort of expression, some function for your error term, and it's a quadratic function even in higher dimensions. You minimize it relative, you minimize that quadratic function. This yields some set of equations that are linear that you then solve for, and then you show that the thing's a minimum somehow. So the general argument, the general proof is probably a little bit harder because, in the end, you have to actually demonstrate that there's a solution to some set of linear equations and some abstract set of linear equations. You have to then show that, the higher dimensional version of the second derivative, has some value. So you look at the determinant of the matrix of partials, if you remember Calc 3. If you're in the right, if you get the right parity for that thing, then you actually are dealing with a minimum. And so, we won't go through the details of that. That's complicated. It's a bit complicated. What I would say about it is if you ever take a course in linear regression, or any course that sort of involves linear regression, at some point people talk about this, the so-called Gauss-Markov theorem, where you're trying to show that ordinary least squares is, say, the best estimator that satisfies certain properties. That's basically what we're discussing right now. So we can find a least square solution if we're dealing just with this one-dimensional case, but most people don't care about that case. The problem that we normally have is a version of trying to project the vector onto a subspace of Rn, which is spanned by more than one vector. We'll describe a little bit about how that might be done. We'll write a formula down. We'll solve some problems in which that occurs. In which such a thing naturally occurs. Then we'll talk about theory of inconsistent systems of equations. So moving on. Oops, moved on too far.
Can you go back one page just real quick?
You like me to show which page?
Just the previous one.
Okay, this one? Not this one. Not that one? That one?
No, one before it.
That one.
Yeah, I just wanted to.
Yeah. So what's being described on this page and the page that follows is not the geometric intuition, which it's not that rigorous, but at least plausible. What you're seeing here on these two pages is how you would actually do it in a careful way. Just using the tools of calculus to solve some sort of minimization problem is the approach that you should take. Trying to minimize some kind of quadratic function. And the more general case, the higher dimensional version of the same thing, a vector projection, is similar. You're just trying to basically minimize some error term. If you take some vector which is not in the span of some subset of vectors of Rn. Is that okay?
Yeah, that's okay. Thank you.
Okay. So the higher dimensional version, the issue that you're confronted with is that you're usually looking at a subspace of Rn or Rm, I guess is ever in here, rather than just one vector. Suppose you take a vector v which is not in the span of S. As before, you want to find a vector u within the span of S, which minimizes the squared error. Since u is an element of the span of S, it can be written as a linear combination of the vectors a1 through an. If you arrange those vectors a1 through an into a matrix A, where the columns of A are the vectors a sub I in order, you can regard U as A times K, where K is a vector of n indeterminates. So this is similar to the case that we dealt with before. Since you're looking for a vector, if you're looking for a projection of A onto the span of a single vector, you know that projection has to be a scalar multiple of B, of the vector B. In this case, it has to be a product. It has to be a linear combination of vectors within the span of S. But for that, just remember, just one note here. I think I'm writing this as matrix A, but if matrix A is, that's column vector, the column vector is A1, the second column is A2, last column, I guess, is AN. Remember that this guy times K1 all the way up through Kn, I guess, is the same as K1 A1 plus K2 A2 plus Kn AN. And so when you're thinking about the vector that you're trying to project V onto, if that projection is an element in the span of S, you're saying that it can be written as a linear combination of the vectors A1 through AN. So you're representing U in this way because you're thinking about a projection which looks like this, which is some linear combination. You're trying to find the values of K. So you want to make a choice for K, but this time K is a vector, which minimizes the squared error. So note the similarities. Note the similarities in the setup. The goal is to minimize the distance between the vector V and the subspace onto which it is projected. That distance, that directed distance, is represented as AK minus the vector V. So you're trying to work out what the minimum value is for that distance. It's a minimization problem, and it's a good deal like the problem we just did, except it will necessarily, I mean, if you think it through, it will necessarily involve some multivariable calculus. We'll look at an example of that, I think, toward the end of class today that's fairly concrete. I don't really want to prove the Gauss-Markov theorem. You can always look that up, or if you wait around long enough or take enough classes in which least squares estimation is used, you'll eventually see some version of it. So, back to the slides. Geometrically, the vector K can be found by realizing that the vector AK minus V is orthogonal to all vectors in span of S. To think about why that is, geometrically, I guess it's the plausible analog of the first thing we did. If you think about it for a minute, you've got some vector which is not, you can think about this just a situation where you have two vectors within, if you have two vectors within the set S, if you think about a vector in R3 which is not in the span, if you choose some point within the span of two vectors within R3 that is at a minimum distance from the end point of the vector V, what you're liable to do is you're liable to pick a vector that's right below the point of V. So you're thinking about projecting the vector V down onto the span of the two vectors. Just mentally, you've got this big plane, you've got a vector sticking out of the plane. The shortest distance from the end of that vector down onto the plane is straight down. It's not in any other direction. So does that make sense? That's all we're saying with that last statement. So, you're trying to think about what vector you would need within the span of the set S in order to ensure that you move straight down into the span of the elements of S. So any vector in the span of S can be represented as a matrix product AY for some set of weights Y. And again, this argument just is based on geometric intuition. And so for all weights Y, you're going to have an equation that looks like this. If you take a vector that's within the span of S and multiply it by this thing right here, you're looking for a choice of K to make the guy that I just underlined point up from the subspace. It points away from the subspace at a right angle. A bit of algebra sort of indicates that you have this AY transpose turns out to be the same as Y transpose times A transpose. You move the transpose in. And, basically I'm flipping this by, I'm reversing the order of multiplication by taking the transpose. I multiply in A transpose and I get an equation of matrices, which looks a bit like this. What I'm saying is that for all weights Y, if it turns out that in order for this vector to be orthogonal to the spanning set of S, anything within the spanning set of S looks like A times Y. So the inner product of A times Y with AK minus V must be equal to 0. You get something that looks like this. And that can only happen if this guy right here is the 0 vector. It occurred to me to actually write down a proof of that. I like the proof I wrote down, but for some reason I erased it from the set of slides, so I'll have to write that down. Even more, if A has linearly independent columns, then it turns out that A transpose A is invertible, so we get a formula for K that looks like this. You usually call something that looks like this the least squares solution. Other textbooks call this K vector that you're finding, this equation, they call it the normal equation. I'd like to talk about this first, and then I included an argument which justifies the last point. We'll talk about that in just a second because it's interesting to see. I like the argument I have for the first point, so I'll go over it. I want to show that if the inner product of V with W is 0 for all vectors V, then W is the 0 vector. So basically, I want to come up with a justification for the reasoning in between this equation right here and this one right here. Basically, this equation right here essentially is giving you the normal equations, the normal equation. Actually, it's the normal equations, I guess, since it's a vector. So why does something like this work? There's probably several ways of seeing it, but I want to look at a particular way. I'm not saying that this is the most efficient way to get to the answer, but I think it is a nice way. It lets me talk about, talk about basis again. So I guess V and W, let's just say they are elements of Rm, some Rm. We can write, so let, just for the sake of brevity, let E1 be with 1 followed by a bunch of zeros. I guess if it's an Rm, you're thinking about M zeros. Let E2 equal to 0, 1, followed by a bunch of zeros. Again, you're talking about M by 1 column vectors. Finally, let EM be the column vector with a 1 in the last position. So when you see something like this, this is known as the standard basis for Rm. So does everyone know what I'm talking about here? So we've seen examples like this if we're thinking about fairly concrete vector spaces. Like R3, the standard basis for R3 would be the column vectors 1, 0, 0, 0, 1, 0, 0, 0, 1. I'm just extending that idea, and I'm kind of giving a name to these so I don't have to write them down every time. The typical notation for the standard basis, you usually write E, the symbol E sub I for the different basis vectors. So E sub 1 is the column vector with 1 in the first position and zeros everywhere else. E sub 2 is the column vector with the 1 in the second position and zeros everywhere else, and so on. So that's sort of the classical example of a basis for Rm that most people want to think about anyway. We can write V, well, we can write W as a linear combination of those vectors, because those vectors form a basis for Rm. So why is this important? Realize that the dot product, that the inner product of EI, EJ is equal to 0 whenever I is not j, and the dot product of EI with EJ is 1 whenever I is equal to j. So again, that's just a matter of verification, but that's pretty plausible if you think about how the matrices are defined. If you were, for example, or if you think about how the basis is defined, if you were to take E1 times E2, the inner product of E1 with E2, what would that look like? It would be 1 times 0 plus 0 times 1 plus the sum of a bunch of zeros. That's definitely equal to 0. And that's true in general. And to convince yourself of this, just notice that if I is not j, then the ones are in different positions for EI and EJ. Usually, so I'm going to put a little dot there. But if I is equal to j, then the ones are in the same position and the inner product is equal to 1. So we wrote down W in terms of the vectors E, in terms of the standard order basis. Sometimes we call C1 through Cm the coordinates of A. So we know W's coordinates. I want to be able to see what's going on with those coordinates. So just consider the inner product EI times W for each I. What does it look like? So the inner product distributes over sums. So it looks like EI times C1 E1, put a little arrow over these, plus C2 E2. We finally find I in there.
What are we trying to find?
I'm sorry?
Oh, sorry. I was just wondering, what
Yeah.
are we like trying to figure out with the like, are we trying to prove that W dot 0?
That's right. We're trying to prove that W is 0.
Okay.
So we're writing down W in a very simple way, using the the standard ordered basis. And so the effect of so the goal here is if you take the inner product of EI with W, what will happen is that will, if you do that for each I, what will happen is that it will identify the weights, it will identify the values of C every time you do this. So this thing right here, because of this property right here, EI times all the guys, the dot product of EI, the inner product of EI with all of these vectors where the index is not I is equal to 0. There's only one vector that survives. So this is equal to CI EI dot EI. But again, from that fact, the dot product of these two vectors together is 1, so that's just CI, right?
Correct. Yeah.
So, we sort of isolate, these things one at a time, right? So, what does this mean? At the beginning of the problem, we're assuming that V dotted with W is 0 for every V. So that's true also for these standard basis vectors. So we've assumed that, so we've assumed something well, yeah. So I won't write that, but EI times W, we've assumed that EI and W, EI, the inner product of EI with W is 0. The inner product of EI with W is also CI. So CI is 0 for each I. What does that mean about W? If you view the Ci as being coordinates of W within the vector space Rm, you're basically saying that the coordinates are all 0. What that means is that W is 0. Does that make sense? It's not the only argument which justifies this idea, but I like it. One reason why I like the argument is that it allows you to talk about a particular choice of basis, which makes the demonstration really easy. If you choose the standard basis has properties which allow you to kind of uncover the truth about this vector W. So a vector W that's orthogonal to everything within the vector space has got to be the 0 vector. That's the only choice. That's plausible, but this is sort of a demonstration of it. You're writing down W in terms of a very easy basis, the standard ordered basis, and you sort of get what you want by thinking about how the inner product of the standard ordered, the standard basis vectors with each other actually work. One more comment about the argument, one more comment about the standard ordered basis. Standard ordered basis is the prototypical, it's the, what word am I looking for? It's the paradigm for something called an orthonormal basis. We're going to talk a great deal more about orthonormal bases tomorrow when we talk about orthonormal basis in the Graham-Schmidt process. But that's for tomorrow. It's the prototype for an orthonormal basis, but it's not the only orthonormal basis that exists for Rm. Orthonormal bases are very nice. Among other things, if you could find some orthonormal basis, it's sometimes easy to think about what the action of a matrix is on a vector space, how the function A works. If you alter the basis that you start with slightly, you can represent that matrix in more easy terms, I guess I would say. But that's probably all I'll say about that for now. So it's kind of pretty far down the page. So let me move back up. The other point, if A has n linearly independent columns, then A transpose A is an invertible matrix. This needs to be justified. I don't know if I want to go through the total justification. I guess what I would say is that that's right here. The fact that A transpose A is invertible in a case like this sort of is explained in this slide. Roughly what I would say about it is it's essentially a result of the rank plus nullity theorem. So if the m by n matrix, if A is such that it has n linearly independent columns, what does that mean? It basically means that the only element in the null space of A is 0 because of that theorem. If you think about it for a minute, you realize that A transpose A also has n columns. So if you're somehow able to show that the dimension of that this dimension over here is 0, then you know that A is of full rank and is therefore invertible. It has enough, its dimensions enough. So we'll see very quickly that n of A consists of the same vectors as the nulls. So that we'll see that the null space of A and the null space of A transpose A are the same set of vectors. Don't really want to go into detail here, but it's probably worthwhile just reading those 2 points at some point and thinking about them. So when we're thinking about A transpose A versus A, when we're thinking about their ranks, they wind up having the same rank, and they're invertible. A transpose A is invertible whenever if A has full rank, if A has n linearly independent columns. The reason why that's important in our formula is because of, the reason why that's important in our formula, if you go back to, I think I went back too far again. If you go back here to this guy right here, sometimes that's also called the normal equations. And so finding K explicitly will involve calculating the inverse of A transpose A. There are some technical obstacles to doing this sometimes. Namely, if A does not have enough linearly independent columns, then that inverse, won't exist. So we'll see this concern show up a bit later. So that's kind of where we're at. Now, talked for a while. I think I'd probably like people to mess around with a particular problem, and it's this one right here. Here's the question. So the following system of equations is inconsistent. So we're thinking of the theory of inconsistent equations. The role of A is played by this guy right here. I think in our setup, the role of B is played by this guy right here. You're trying to find the values of U and V. I guess what I would say is use normal equations to do this. So again, the normal equations appear sorry. They appear right here. So the value of K that you want, the U and the V that you want in that problem will somehow come from this, will somehow come from this equation right here. So take a moment to do it, take 2 or 3 minutes to sort of find the value, find the so-called the least squares solution to this inconsistent system. Maybe first show that the system is inconsistent, then try to find the approximate solution. Your problem, if you're looking at the system of equations, how would you show that it's inconsistent? It doesn't have, so I mean, again, how is inconsistency detected in this case? So in this particular problem, you won't have a solution to the system of equations, and it's pretty easy to see that. So if you think about the augmented matrix, that will produce the solutions of equations, I think you will find that this is row equivalent to something that looks like this. How would you get that? You eliminate the 1 that you see here by taking -1 times the first row and adding. So what you're seeing with inconsistent systems is that you have a 0 row and then a non-zero number in the solution column. So there's no actual solution to the system. You can't write one down because there isn't one. The next best thing to solving an inconsistent system is to produce a solution to the system, or an approximate solution to the system that minimizes the error. The error in this case is defined as the distance between the column space of the matrix that you're dealing with, matrix A, and the vector B that you're trying to solve for. So, we don't need to use calculus to do this. We can just use the normal equations. And so the approximate solution that we're looking for just looks like something that you would get up here. So just multiply, so find A transpose A, which is a 2 by 2 matrix in this case. Find the inverse of it, multiply it by A transpose, and then V is the vector on the right-hand side. That's the approximate solution. So that's really all you have to do in this problem. In this case, just use the normal equation to come up with the approximate solution. So that's the least squares method. One reason why you want to encode. So you'll notice that there's some ambivalence about how to actually show that that the least squares solution is what it is. It's not really a solution; it's just an approximate solution. But there's some ambivalence about how you show it. If you're thinking about the least squared solution from the point of view of calculus, you're minimizing some error term, and theoretically, it's actually pretty nice. You can write down some reason why you think you actually have some minimum. but computationally, it's not so nice. How are you going to get a computer to take a derivative? I mean, how do you actually code in an algorithm which would produce a least square solution given a large inconsistent system of equations? The reason why you see this formulated as the reason why you see least squares formulated as a solution of some kind of matrix equation is because matrix equations are understandable by machines. So there's an algorithm that you could sit down and write into a computer that will produce a least square solution. So anything that can be encoded with the matrix, like what we're talking about right here, is absolutely something that a computer can understand. The matrix solution generally depends on understanding a little bit about the geometry of Rn. The calculus solution is more analytic, but probably not that practically useful. So being able to find a least square solution by hand using calculus, no one's actually going to do this. If you have like 50 equations and 2 or 3 unknowns, you're not going to sit there and work out the solution to a bunch of linear equations in order to find the least square solution. You're simply going to type it into a computer. Luckily, the algorithms that the computer possesses via matrix multiplication, basically, are such that it can compute the least square solution directly. So in practice, you'll probably never be doing this by hand. But if you want to understand what's going on behind the hood, when you actually ask a computer to come up with a least square solution, that's what it's doing. A couple of other broad points. So I skipped over an example, but just did that in the interest of time. What I want to talk about, or at least give an overview of briefly, though not, I don't think we'll have time to do the problem, but we'll see. When you write ordinary or classical ordinary least squares in statistics courses, there's a method that is introduced, maybe not explained carefully, but not like this, but it's introduced where you're trying to come up with the so-called line of best fit. And that's kind of why people generally talk about this sort of method. The context for using the method is you usually have a couple of quantities if you're dealing just with the line of best fit. There's some explanatory variable and a response variable. And you gather data, maybe you want to measure height and weight, figure out how they're related. So you have an explanatory variable and a response variable. People are going to tend to use maybe height as explanatory, weight as response, or vice versa, to think about the relation. Probably not vice versa, but in any case, if you think that the explanatory variable and a response variable are approximately linearly related, then using the least squares method is plausible. You might have some measurement error, you might have some missing inputs, things could go slightly wrong, but you're thinking that the relationship between the explanatory and response variable is very roughly expressed by a linear equation, y equals c plus dt. So practically speaking, the goal is to try to come up with what c and d are using the data points themselves. The problem is to find the values of c and d. So if it's true that the explanatory and response variable are truly linear, the relationship is truly linear, then there's no problem at all. Because if it's truly linear, you only need 2 measurements in order to come up with a line through them all. The thing is, there's always measurement error. So practically, you will never find a situation in which you have a truly linear relationship. Lots of things are quasi-linear, pretty close, but measurement error always intrudes. And so probably, so for the most part, you're always finding, even if the relationship is linear in some moral sense, you're always finding lines of best fit. So how does it actually work? What we're saying is that if we think that the relationship's linear, we have a large system of equations. So we have pairs of observations, t1, y1, t2, d2, and so on. We plot them in the plane, in the ty plane. And if we think that t and y ought to be linearly related, we can encode these pairs of observations as a sequence of equations which look like this. Now, the truth is, there's absolutely no way in practice that a large system of equations like this is going to have an analytic solution that you're going to actually be able to sit down and find C and D. The system of equations you're talking about is almost surely inconsistent. And so the best because usually, you have like 100 observations. So like M is something like 100, but you're really only looking at, in this case, like a bunch of linear equations, right? So you have two indeterminates, C and D. but you've got like 100 equations, like, or some huge number of equations which give you the relation. So instead of trying to actually find the line, which is going to be hopeless, you're basically just looking for a least square solution to the matrix form of the equation, which looks like what's below. So the role of the matrix A in least squares is going to be played by this guy right here. In the normal equations, the role of K is going to be played by this guy right here. And I think in the normal equation, I wrote this down as V. So if you're looking for a least squared solution, again, there's a way to do it very quickly. You just use the normal equations and you get your answer. So the formulas that define least squares come from that. You can use the normal equations to come up with a least squared solution. Normal equations give you something that looks about like this. As long as the matrix A has linearly independent columns, we can make sense of the inverse of A transpose A and solve the system for C and D. The least squared solution that you get is what C and D are when you look at the normal equations. The problem with the method, of course, is if the matrix A does not have linearly independent columns, in which that's where things can get screwed up. So you don't really have even an approximate solution in a case like this. It's kind of a major technical obstacle to using least squares. So collinearity is an issue. When you're talking about least squares, sometimes that's brought up in stat, but usually you're just thinking about interpreting the result. What's going on behind the hood, if you think about least squares approximation, is you're just using the normal equations to try to come up with an approximate solution. It's just a much larger version of what we've already done, where you're trying to find the projection basically of some vector into some column space. The matrix A spanned by is got two columns in it, so it's flat, and so you can draw a picture of it. In lots of cases, you're trying to find C and D, which project down onto it. That's the best solution. You're never going to find the exact solution in cases in which least squared is used, because you're never going to have exact linearity between all those equations. So there won't really be a C and a D, in the algebraic sense, which gives you the answer. So linear algebra doesn't help with that, but it does help from the point of view of being able to come up with a reasonable approximate solution, which minimizes some error term. A couple of general points about it. The error term that you're dealing with is, again, quadratic. If you actually sat down and wrote down what the error term is, you get this big quadratic expression. When you try to minimize that, you have to solve a bunch of linear equations, which come from the derivatives, the various partial derivatives of the quadratic equation, the quadratic expression that you're trying to minimize. And so, trying to show that you have an approximate solution via calculus, to be honest, is pretty hopeless. Like, you're not really going to do that by hand, but a computer can do it very quickly. And in fact, there are algorithms that you probably used in the past that work under the hood to produce least squares approximation, but it's all matrix. It's all solving matrix equations quickly via computer. That's how the coefficients are produced. So it's an important application. But to be honest, you're never going to do it by hand. So I was going to have people do this exercise when you're actually trying to find the least square solution. I think probably I'll defer that particular exercise to the written assignment, where you can kind of work out what the least square solution is using the normal equation. It's a dumb, in a sense, it's not a great example, because you have measurements t and y, but you're never really going to have only 4 of them. If you have hundreds of these things, you're obviously not going to do it by hand. So I'm sort of ambivalent about even assigning it, but it's nice to sort of practice matrix inversion anyway. So one technical issue I'd point out about the normal equations is that if the matrix A has, see, it's got 2 columns, if those columns are not linearly independent, then you're going to have a problem. That's going to result in a situation where the system that you're dealing with is insoluble, even in an approximate sense. Moving through. I had an idea maybe to talk about calculus a bit more. To be honest, again, I might reserve this for the written assignment or a version of it. Yeah, I mean, I think that's probably a good idea at this point. So this particular problem, I think I'll just sort of give you to work on during the written assignment, as you're working on next week. It's a reasonable problem. You're trying to, so there's one correction I should make. Should be minus. So might give this problem on the written assignment for you to work on. You can calculate the least squares solution that basically amounts to finding out the u and the v, either through the techniques of calculus, which in this case are pretty straightforward, or through using the normal equations. I've talked a lot today. There's one more thing that I think that I'll discuss. It's only one slide. One last thing to discuss that we're going to get into in more detail tomorrow. One final topic for the set of slides. If you let the x bar denote the approximate solution, we've basically written that ax bar is the projection of B onto the column space of A. It turns out that the normal equations are basically stating that this matrix right here is the matrix which does the projecting. So that linear transformation applied to, in the previous example, applied to R2 is going to give you or either applied to R3 is going to give you what you want. It's going to map B onto the column space of A, so that projection matrix is written as A times A transpose A inverse times A transpose. It's this big matrix. So it turns out that as a class of matrices like this particular matrix we just identified are a really important category. We'll be able to see that any symmetric matrix can be decomposed somehow into some set of projections. Formally, you define any projection as a matrix that has two properties. P squared is equal to P, and symmetry. So P is equal to its own transpose. So I guess it's going to be square, right? And exercises to show that a matrix, the matrix which projects B onto the column space of A is a projection. Again, I think I'll probably leave that for the written assignment rather than doing it right now. It's sort of a straight. It's a question of analyzing symbols, I guess, most of all, but maybe that's a question that's best left for the third written assignment. That's the last thing I want to say. I think today I've talked a lot. Information I think is a bit overwhelming at this point. But again, the takeaway from today, all we're really doing is we're exploiting the notion of distance on R2 to come up with a theory of inconsistent equations. That's it. So we know already that if you have something that looks like AX equal to B, that equation is going to be inconsistent if the vector B does not lie in the column space of A. And so if you have an inconsistent system, it's usually revealed by some row reduction from a practical point of view. So what's going on today is not going to help you solve those exactly, because that's impossible. But instead of solving them exactly, what you're doing is you're coming up with an approximate solution to the equation. So you're basically finding a vector K, or you're finding a vector. Sure, I'll call it X or K or something like that, which is close enough. You're finding a vector K which minimizes some measurement of error. So it's not really a solution to the equation, but it's an approximate solution to the equation. And the reason why you're doing something like this is because in practice, your linear systems will never, they're almost never soluble in the exact sense, particularly if those linear systems are overdetermined. If you have many more equations than variables, it's almost certainly not the case that you're going to be able to come up with some sort of unique solution to the associated system of equations. The next best thing is an approximate solution, and the typical method that people use is least squares. So I think at this point, I think I will end the conversation. It's over right now. I don't really have anything more to say about this. I'll reserve some of the problems, I think, on the slides for written assignment 3, the ones that I think people can do by hand. And I guess that's about it. I'll stay around for 5 or 6 minutes if people have any additional questions. And if not, that's okay. I'll have an office hour later today. So hopefully I'll see you then, or either then or tomorrow.